And it also took NASA $20 million to recover from this fire in terms of redesigning the suit.
Extravehicular activity is dangerous for many other reasons as well. In fact, the world's first spacewalk almost ended in disaster.
Alexei Leonov did the first spacewalk that any human did in 1965. But in the rush to accomplish that space spectacular and thereby beat the Americans, the Soviets took some shortcuts on the safety of the cosmonaut. And so he blew up like the Michelin Man.
The suit became rigid. It couldn't handle the pressure differences between the breathable atmosphere inside and the vacuum of space.
The problem is you've got a spacecraft in the Soyuz capsule that he was flying that's very small, and the hatch for it is even smaller. Ultimately, his response was to let a little bit of the air out and just deflate the thing enough so that he could crawl back in through the hatch. But he will tell you that to this day, that he wasn't sure he'd be able to make it.
An astronaut having, like Leonov, to let the pressure out in order to be able to maneuver in it is in the same situation as a diver ascending from deep water too quickly. Nitrogen bubbles will form in your bloodstream and not only be painful, they'll kill you.
And during EVAs, a simple thing such as an unsecured tether or a misfiring emergency thruster can also spell disaster. Being outside of a spacecraft on a spacewalk is the most dangerous thing an astronaut in orbit can do. One false move can be deadly, especially if that false move takes you away from the spacecraft.
There was an instance on one of the Russian space stations, the Soyuz, where one of the crew members was not tethered and he was in the airlock area watching the other crew member, and he slowly started to drift out, and the other cosmonauts saw him and grabbed him. An untethered person in space without appropriate propulsion system to get back would be very, very serious. I mean, basically, you're lost at sea.
Even with a propulsion system, it can fail or run out of its limited propellant supply before the astronaut reaches safety. The astronaut will simply keep floating off into space. The International Space Station is unable to chase someone down, and if the shuttle were docked, it would take too long to undock and mount a rescue. In this nightmare scenario, the astronaut will likely have several hours of oxygen remaining to contemplate the end. As long as the suit is intact, pressure will not be an issue. Either the oxygen will run out, or the system, which removes exhaled carbon dioxide, will stop working. Either way, the astronaut will suffocate and continue floating into the emptiness of space. The same micrometeoroids that can devastate space colonies also pose a lethal threat to spacewalks and entire spacecraft. Plus, in low Earth orbit, these rocky little gremlins have company: space junk. And all of these things are racing around at over 22,000 miles an hour. At these speeds, objects that are only a fraction of an inch wide can be deadly.
A micrometeoroid flying through space is a lot like a golf ball flying through the air, with these differences. The micrometeoroid is much, much smaller. And because it travels at hypervelocity, it's far more destructive when it hits. If a micrometeoroid hits your spacesuit, it's going to put a hole in it. You don't have reach or the ability to patch or fix it, unless you've got a fellow astronaut right there. You're going to die. Your air is going to leak out fairly quickly. It's going to gush out. Your blood's going to boil. That's going to be it.
And what causes blood to boil? Well, in space, boiling blood has nothing to do with heat. It's all about the sudden lack of atmospheric pressure.
The idea that blood boils is really a misnomer. The liquid in your body goes from a liquid state to a gaseous state.
There have been many tales about what happens to an unprotected person in outer space. Here's the real story. As the vacuum of space fills the spacewalker's leaking suit, the liquid parts of the tongue and eyes begin to bubble. along with all of the saliva, internal fluids, and blood. As the blood turns to gas, oxygen no longer travels to the brain or anywhere else. The brain shuts down within about 15 seconds, leaving the victim unconscious. Soon after, the rest of the cells in the body die. Temperature extremes could also play a role, since the sunlit areas of space reach 250 degrees Fahrenheit, and the shaded areas quickly plummet to 250 degrees below zero. And just how big a hole is too big for a spacesuit?
You're really asking a very small amount of material to stop a particle that could be coming in at 7 kilometers per second. You can see the entry hole from the test, and it has many, many layers, ending with what's called the bladder. And this is a pressure retaining layer. That's about a 2 to 3 millimeter hole, a 4 millimeter for an EVA suit on the soft goods. This material would be considered catastrophic.
Luckily, no one in space has ever suffered this fate. Impacts can also cause trouble in sneakier ways. So NASA goes to great lengths to simulate different types of micrometeoroid damage down on Earth. Researchers inside the hypervelocity building of the White Sands Test Facility in New Mexico create impacts using compressed hydrogen gas guns. These guns definitely bring the heat, shooting objects up to 19,000 miles per hour at shuttle and space station parts to assess the damage.
At that velocity, you can get from Los Angeles to New York in about 8 minutes. The testing that we're going to perform today is on an International Space Station handle that the astronauts use on the outside of the space station in order to transverse around the space station safely. Several astronauts have cut their gloves severely. This is a great concern to NASA because when they design the space station, they are very careful to eliminate all sharp edges because you don't want something snagging the astronaut spacesuits and creating a hole and ending a mission.
Technicians mount the handle in the target chamber, place the tiny 1/32 of an inch wide projectile within a holder that will disintegrate once fired, then add gunpowder to the breech.
We take gunpowder and propel a piston which compresses hydrogen gas up to about 100,000 psi. It's that highly compressed gas that accelerates the projectiles from 0 to 19,000 miles per hour. We use 3 different types of cameras. One takes a snapshot, another one takes a film, and the third type is a digital camera which takes 16 frames at 200 million frames per second.
The technicians retreat behind a blast shield and prepare to fire. The chamber is cleared of oxygen and other gases to simulate the vacuum of outer space. Now, the moment of truth. How much damage did this simulated micrometeoroid cause?
Even though it is a small impact, there's enough of a lip with enough structure so that an astronaut could catch their glove on such a lip and cause a tear in their glove.
And if a projectile only 1/32 of an inch wide can cause this type of damage, you won't believe what a larger object can do. At the NASA White Sands Test Facility in New Mexico, researchers load small projectiles into huge guns.